Question 1. Give the sample space of an experiment consisting of drawing a card from a standard deck and recording its suit. Well, our sample space is hearts, clubs, diamonds, and spades. That's all the different suits you can have when you draw a card out of a deck of cards. Number 2. A red die and a blue die are rolled, and we want to know the following. Now, it's a dice problem, so let me make my dice chart here. So there's 1, 2, 3, 4, 5, 6. That's my blue die. On every dice problem, draw the chart. Makes your life easy. Or easier. Each one of these boxes corresponds to a different roll. Now part A says, list the event A, the sum of the numbers on the two dice is odd. So if I go through my chart here and put a little dot, I will mark all the ones. So this has a sum of 2, that's a sum of 3, a sum of 5, a sum of 7. So, oops. In the right spot. So all of these that I have marked in these little dots here are the ones that have a odd sum. Now in some dice charts you'll see that the sums are actually written in here. And in my ordered pair I'm going to write red and then blue. So my first pair is a 1, 2, 1, 4, So there's our set A. I've listed every one of those dots in my chart here. Now, notice the 4-1 and the 1-4 are different outcomes because of which die they came out of 4 and which die came out of 1. Part B said, list the events where the sum is less than 5. So I'll put a green dot in these. All the ones that have a sum less than 5 have the green dots. And the next part of this question says, are A and B mutually exclusive? Well, mutually exclusive means they have nothing in common. Quick look at our dice chart or look at our sets, we notice that there are 2 of these things that have both a light blue dot and a green dot at the same time. So the answer is no, it's not mutually exclusive, because these outcomes I've underlined in blue happen in both sets. Part C says, list the outcomes of A intersect B. And that gives us our results. Question 3. A family has 4 children. Give an appropriate sample space for this experiment. Well, if you think about it, you could have had four boys. You could have had the first 3 boys and the last one a girl. And if you continue this pattern, you'll get this entire chart. So we have our entire chart here And our sample space is actually this whole thing. Now, how many different outcomes in our sample space? Well, think about it, it's 2 to the 4th or 16. Now, part B says give the sample space for the event B where the oldest child is a boy. Now, if we take our first column being the oldest kid, the last column being the youngest kid, our sample space, our event B, would be all of these that I've highlighted in yellow. Question 4. Jim has a drawer containing 8 blue socks, 5 black socks, and 6 white socks. He pulls 2 socks out at random. What's the probability Jim will have a matching pair? Well, you pull 2 out at random. You're not concerned about the order, so that means combination. You're not returning anything, so we have combination in this sense. So, both blue, combination, 8 choose 2. Both black, combination, 5 choose 2. Both white, combination, 6 choose 2. Divide it by the way of pulling out any 2. So 8 and 5 is 13 plus 6 is 19. And you get combination 19 choose 2. Question 5. Box contains 4 red, 5 white, and 8 yellow marbles. What's the marble is drawn? What is the probability the marble is red? Well, it's 4 red over 17 total. Part B. Assuming the first marble is red and is not replaced. Okay, that means we now have 3 reds left. What's the probability the second marble drawn is red? Well, there's 3 reds left. The first one wasn't replaced, so now there are only 16 marbles in the bag. Part C. Assuming the first marble is not replaced, what's the probability that a red marble is not drawn in neither the first nor the second draw? So we're drawing 2 marbles, not replacing them, and neither of them are red. So if you think about this, 5 and 8 makes 13. So on the first draw, there's 13 things that are not red out of all 17. The second draw, now there are only 12 marbles that are not red, and there's 16 marbles that are still left. So in essence, what we've done is a tree for part C. We have a tree, we're talking about red and not red. And we're looking for this branch. And we're computing this branch here. You could have done red, white, and yellow, all 3 different branches. You'd find all the branches that don't have any red on them. Number 6. 5 coins are tossed. What is the probability that exactly 2 of them will land heads? Well, first of all, how many ways can you get 2 heads when you toss 5 coins? It could have been the first 2 coins, the first and second, or the first and third, first and fourth. In essence, combination 5 choose 2 will tell you how many different ways 2 of the coins can be heads and the other 3 be tails. The 5 choose 2 says of the 5 tosses, pick 2 to be heads. Now we divide by how many ways can you toss the coin 5 times. Well, each toss has 2 choices. Divide by 2 to the 5th. When we get to chapter 8, this problem can be worked with the Bernoulli problem. This is, let's just say 8.4. In this case, n is 5, p is 1/2, and r is 2. So, little note for the future. That's another way of working this problem. We have 2 weather forecasters, one at station WIVV and one at WILA. and they each have a different percentage chance of being correct. Now, one person making forecasts will be independent of another person. In other words, first person being correct is not going to influence the other person. Now, we want to know what is the probability on the given occasion that one of the two or both will be correct. Well, in essence, we're drawing a tree. The first guy is correct or either incorrect, and the second guy has the same information. First guy is correct 82% of the time, and incorrect 18%. Second guy is correct 65% of the time, and incorrect 35%. Now we're assuming independence on here. In other words, we're saying that the first person being correct is not going to affect the chances of the other person. And we want to know what is the probability on a given occasion that one of the two or both of them will be correct. So if we look at our tree, one of the two or both, we want every branch that has a C on it. So in terms of our answer, this is 0.82 times 0.65 plus 0.82 times 0.35 plus 0.18 times 0.65. So these two are only one person correct, and this is both of them being correct. Now, if you look at this problem, you could have also thought about it and said, well, notice the only branch I don't want is this last branch here at the bottom. In other words, it's the one minus the probability they're both incorrect. So 1 minus 0.18 times 0.35. So this is method 1. This is method 2. Method 3, if you want to do this, you could have said one or the other or both. That's a union. I'll use the V and the A. So V union A. So probability the first person's correct is 0.82. Second person's correct, 0.65. Now minus the probability of the intersection. Because we're using independence, the probability of V intersect A is the probability of V times the probability of A. If you don't have independence, that's not true. So what we have is 3 ways to work this one problem. Now we'll go to the next problem, which is nicer. If Nancy selects a security from a list of 3 growth stocks, 7 income stocks, and 5 bonds, what's the probability she'll select a bond or a growth? So, bond and growth, so there's 8 of them. And how many of them are total? There's 8 and 7, 15.